Now you can.
All right. Looks like it did it.
Okay. So thank you everyone for coming today. Alan's not here. Mary is going to be helping answer, watching the chat or helping with questions. And next month, the same time, 2 p.m. Pacific, on the 3rd November, the third Friday of November, which is November 21, Alan Gould is going to have the second in his series of planetarium educator workshops. This module will be on a framework for examining planetarium programs. So that's the third week in November. And then when we do a seminar in December, it'll be on the second Friday. We don't, we do have a sign up. It's in the chat. So if you could put your name and where you're from there.
In
Our speak
December is me.
and December's Mary. If you have a title, you can give it now.
Oh gosh, what did I land on? I think it was people management for the planetarium or something along those lines. Yeah.
Yeah, that's right. So you get the idea. So we'll go ahead and start with Richard's talk. Rick is the chairman of the Department of Astronomy at Cabrillo College, which is in Aptos, California. He's also a member of the Earth Futures Institute at UC Santa Cruz. Um, he makes observations, so he must be an observational astronomist. He's determined some of the masses and shapes of asteroids. He's discovered some moons around Kuiper Belt objects, and he also works on the Hayabusa mission in Australia. So, uh, one of his other interests is in climate change. So, Richard, if you want to go ahead and start, that would be great.
Okay, so can everybody hear me okay?
Yeah.
Okay, good. So let me do a screen share here. Let's see if I can do this. Um, and we'll start the slideshow. Okay, does that look good? Everybody see that?
Looks good.
Okay. Yeah, so we have a A3P planetarium at Cabrillo College, and it's pretty simple. It does work. We've got a nice new xenon light, and it shows the stars very well. But we don't have a lot of special effects. Frankly, I feel always a little bit intimidated when I'm around Carl because he was he was head of one of the best planetariums around, and got that going at De Anza. $1 million setup. We've got something that was put in the 1950s. And so what I am leading up to is, in order for me to do shows that keep young people entertained, I've got to make it more personal. So the planetarium shows that I do are very, very interactive. I walk around the planetarium dome, or not the dome, but I walk around the projector and actually engage the students in the dark light there and ask them questions, and easy questions. Okay, I mean, like questions that they are always eager to ask about their favorite planet and stuff like that. And it's worked pretty well. The kids always seem to be really really good. I think adults would probably say, well, where's all the special effects and where's all the explosions and the it's like, well, um, okay, but let me just go on here. So, first of all, I want to give a big thanks to the Pacific Planetarium Association for a grant that allowed me to purchase a laptop that would then allow me to replace the Kodak Carousel, which had been my projector for many, many years. My budget here at the Cabrillo, which is a small college, is not very much. So even just getting enough for a laptop was very gratefully accepted. I'm out of the Kodak carousel age, thank goodness. Yeah, there it is. So a fairly simple little planetarium, but still, it always feels good to walk down into the planetarium because I've been doing it for almost 40 years now, and it's like a connection with the past. But not everything about the past was super great. I will say this though, that even though the transistors had not been invented yet when my planetarium was made, we have not had a single vacuum tube die during my 40 years at Cabrillo College. Unbelievable, but true. And then I want to give a great thanks to Carl, who I guess you all know. He was my former lab assistant back when I first joined Cabrillo, and then went on to Greater Things. And he's only not only been a great help, but he's been a benefactor to the planetarium when we needed some repairs to get it back going again. So that's me and Carl's in the room there somewhere. Hands-on work a couple of years ago to try and get it all working again. So yeah, it's an A3P, special effects minimal and not working. So what I do is live interactions and impromptus with the slides, and the kids seem to have a pretty good time with it. Like showing cool stuff like the happy face crater. Even though, well, actually, you know what? This slide actually is kind of appropriate for Halloween because he looks about like that big character, remember, in that Steven Spielberg movie, The Goonies. We all remember that movie. A little scary. But then I take him on a tour through the solar system. And I do get a mix of ages. So sometimes I'll have older students and sometimes I'll have very young ones. And so I put in a mix of slides of kind of different level. This one may be a little bit higher level, but you know what? It's really colorful. So they like it. I do have some music going on in the background. Brian Eno, On Land, is my favorite. And of course, we've got to relate things to the students' own experiences. So a video of this shows it looks a lot like oatmeal, okay? And it behaves like oatmeal when it's still cooking. So that's kind of cool. And I tell them they're all about the size of Texas, all those granules. Okay, and here's a picture of the sun. X-ray eyes looking at the sun would see this. So I tell them that you need 1,000,000 degrees in order to give off X-rays. Pretty high power. And now, one of the cool things that everybody gets interested in, no matter what their age, is eclipses. And so I always make sure and tell them what are the next eclipses. So lately, of course, we have the total eclipse of the moon coming up in the United States in March. There was another total eclipse of the moon in September, but we couldn't see it. And we've had a couple of really nice solar eclipses. Unfortunately, there aren't any more even partial solar eclipses that we see in the United States for quite a few years. But I was lucky enough to bring out a telescope at Cabrillo, and we saw the April 8th eclipse a year ago. And I was even luckier. I was able to get a van from the van pool at Cabrillo, and I had one of my students and we all piled in the van, and we had a big expedition out to eastern Nevada to try and get some cool pictures of the annular eclipse. And then we start heading through the planets. So here's Mercury. And I like to stress that Mercury has shrunk. It's just like a raisin in the sun, getting shrunk by somewhere between 6 and 10 kilometers is what the astronomers have figured out. And that's what you would do too, I think, if we baked you at 600 degrees for a few billion years. And then Venus, of course. So we have to start out with, well, how do we name Venus? Well, goddess of love and beauty. It is such a beautiful planet to see in the sky. And so then I hit him with, but when we actually went there and we sent radar through the clouds to see it, it turned out to be an eternal hell. a blistering hell, even hotter than Mercury. 100,000 volcanoes spewing lava everywhere. The runaway greenhouse effect gone wild. So it's always good to give them a little scare. They always seem to like that. And then I tell them to beg their parents to take them out to the big island of Hawaii. Of course, then the parents that are in the room are usually getting squirming in their chair a little bit at that. But so, of course, there's one of our few pictures of the surface of Venus taken by the Soviet Venera spacecraft. And I have been to Kilauea, and that's pretty much what it looks like on the floor of Kilauea, at least when it's not erupting. And then I try and give them, the truth about the fact that while it's fun to go to other planets, maybe even if it's just virtually, this is the only planet that is home, and it's the only planet that we're ever really going to be feeling good at. So even if we somehow set up a base on Mars, I think after, my opinion is after about a month at most, we're going to be begging to come home. It's like, there's nothing here but rocks. I want to go home. And so we got to take good care of it. So that links up a bit with my work with the Earth Futures Institute at UC Santa Cruz. Of course, even nice planets get knocked around sometimes. So we got swamped with a big asteroid. Um, and this is a bit of a prequel to me talking about asteroids, which is a branch of science I'm pretty active in lately. And why we got to keep track of them, because you never know when they're going to come after you. But actually getting hit long, long ago was a very good thing, as long as you weren't there, because it's added a lot of heat to the interior Earth. And that heat has enabled us to keep a very thin crust. And the thin kind of Chicago style pizza crust is really good for enabling plate tectonics and the ability to bury over long, long periods of time, slowly, but bury carbon dioxide, which is, of course, a greenhouse gas we're having trouble with lately. And it does break up the earth into all these plates, kind of like a boiled egg, hard-boiled egg that you accidentally drop on the floor. Except they keep moving after that. And that big collision, of course, is what we owe our moon to. So we love our moon. It's lights our night sky, and it's a great thing to look at. And it's also more practically, it stabilizes our rotation axis. So it always points 23 degrees plus or minus a degree. And that's very good for long-term climate stability. Mars has not had that advantage, and so its axis wanders all over the place. Not so good. And I always like to show this photo. It's a classic because it shows just how, the moon's really pretty, but you wouldn't really want to live there. Okay? It's dead, not like the colorful Earth. So onward to Mars, and we show the giant Valley Marineris and how it drained the highlands of Mars down to the low northern areas. And there's that happy face crater again. Now, a lot of these craters, a lot of these pictures, I did not have access to when I only had slides. I mean, unless I would try and get some old Kodak film somewhere and try and shoot slides, but that's not what I wanted to do. I wanted to just do them digitally and size them the way I want. Um, so then we talk about how we've actually visited Mars and look for fossils on Gusev crater here, which of course we visited with the rovers because it looked like it was full of water at one point and probably had our best chance for finding any fossils of ancient Martians. So there we go, spirit and opportunity. Heading off to go dune buggying across Mars and radioing back all the cool stuff. Cool stuff like sedimentary rock, which showed that, yep, we were right. There was a bunch of water there, showing the way you get sedimentary rock. We did not see any fossils embedded in the rock, but we at least know that Maybe if we go back there and look harder, maybe we'll find something. Anyway, Mars definitely had an ocean, of course, as you all know. And then I talk about this brief moment of, I guess, hubris from NASA, claiming maybe to have found a worm on a rock from Mars. And then the geologist said, well, we know the ways to make things look just like that without any life being involved. And so it's probably not evidence of life. And the whole hoopla kind of died down after that and hasn't come back. We have no evidence of life yet anywhere else in the solar system. But we do have this giant volcano. They like seeing that because it's way bigger than Mount Everest, and in fact as big as Arizona, and how we contrast that with the Hawaiian Islands and how those are also sitting over a hot spot, but the Earth's plates are moving, and so we pop up different islands. And if you add up all the Hawaiian Islands and glom them back into one big mountain, it might look as big as Mount Olympus. And then, of course, the two small moons, which are kind of fun to look at, but yeah, they'd both fit inside my home, Santa Cruz County, with plenty of room to spare. So calling them moons is almost a little bit too much. They're both probably captured asteroids. So here's another lead into what I'll talk about in the second half today, and that is how do we figure out what asteroids look like and what their masses are and their shapes are? And the biggest of them is Ceres, which has these bizarre white areas on them, which people had a lot of fun with, including me, to my classes. Alien cities on Ceres, oh my God, probably not. We hope not. We don't want aliens quite that close, not unless they're friendly. But most movies seem to indicate they're not. So, um, yeah. And so, what do you do with asteroids? Well, one way to try and figure out what asteroids are all about is to take advantage of the fact that the Gaia mission has now got the positions of stars to such a high precision that you can use those stars and the fact that asteroids move really, really, really slowly across the sky to turn that into a very high resolution contours, outlines for the asteroids using occultations. So this is actually me and your friend Carl there and Kirk Bender. And we all got an occultation by this asteroid, which is clearly not round. Back, when was this? This was 3 years ago now, almost 4 years. And we can also do even better if we can measure the changing brightness of the asteroid and then throw a whole bunch of math at it. So this is my little plug to get people sold on how good and how fun math is. We don't want our young kids growing up thinking math is terrible, no matter how bad their teacher might be in grade school. You can do all kinds of cool things with math, including calculate at least a finite number of different models for how the shape and albedo and spin of the asteroid can be to account for the brightness changes that we see. And then we can go out with actual occultation people like, oh my God, look at this, Nolthenius and Bender, our crack team here at Santa Cruz, the core of our crack team. But we've also got a few other members now, including Carl, another couple of Californians. And so we got a pretty good data on this asteroid here and confirmed, narrowed down the solution set to one set. So now we know this asteroid quite well, Medea. Why do we want to keep track of asteroids? I tell the kids, well, because you got to keep your eye on them at all times, just like we have to keep our eye on you kids because you never know what you're going to do if we're not looking. But look at this. So we saw this meteor burning across the sky in the eastern United States is back in 1994. And we threw a bunch of math at it and we said, yeah, you know what? I think this thing came down near Peekskill, New York. Let's go there and see if we can find the asteroid. It looks like it was pretty bright. I'll bet it survived. Part of it survived. So they arrived there and I tell them, what did we find? We found a teenage girl crying. Of all the cars in all the world, this asteroid piece lands on her car and totals it. Now you can tell though, it didn't take very much to total this car because it was just an old Impala, not like a good car. And then I tell them there's a happy ending to the story because she actually got paid more money if they would haul away her car to the Smithsonian Institute and the asteroid than the car was worth in the first place. I need some water. So sometimes you do get a happy ending to stories. Okay, so we're transitioning now into what I am doing with my sort of my professional time and my fun time, and that is chasing after shadows of asteroid because it is scientifically valuable. It keeps me off the street. It gets me out of my house, and it's fun. So this is actually a picture taken at Fremont Peak Observatory, where I got time to go up and watch an occultation by Pluto, which you will see in a moment. So how do we get this to work? Well, asteroids move super slowly, only about 20 kilometers a second. I know that sounds like a lot, but if you're 200 million miles away, it turns into a very, very tiny angle. And we can slice time really, really rapidly and really accurately down to 10,000th of a second and better. And so you combine those things and you can timestamp every frame on a video, and you can see when that star is getting covered up by an asteroid and it winks out, maybe only for a few tenths of a second, or maybe for a second or two or three. That's the typical duration for one of these occultations, and then it comes back. But if you get good data on a decently bright star, then you can combine that and get pretty high precision, better precision than you can get with even the biggest telescopes in the world. Because even in the biggest telescopes in the world, asteroids are too small and too far away, and all you see is a dot of light. After all you need is math. There's that word again. And if you combine that with other observers, then you can get some pretty good data. This particular event here was good enough reason to apply for a van at Cabrillo College and send us off to the bristlecone pine forest in the White Mountains and an attempt to climb White Mountain, which we pretty much did, but we didn't quite get to the top before we felt we should turn around. Um, and again, this helped to reduce the different solution sets for the photometry models to the correct one. So now we got this asteroid all nailed. The Gaia mission, of course, has super precise down to a milliarc second precision for the positions of stars. And okay, damn it, I have to be sure not actually say that to my young kids, but it does it's an acronym and it has to do with getting the exact brightness of stars over time. And that project has enabled us to get at least a good idea of the shape of asteroids. And for very high importance events, NASA and JPL will actually pay you and even outfit you with telescopes to go out and get these occultations. And if you can discover a moon of an asteroid, well, now it's way more valuable because now you can use Kepler's third law, p squared equals 4 pi squared a cubed over g times m, the mass of the system. And we can find the mass of the system. And if you got the mass of the system and then your timings allow you to get the size, well, you can throw those two things together with math again, and now you've got the density. So now you got a pretty good idea of what it's made of. Not just sitting on the surface, which might not be representative of the total asteroid. The total surface of the asteroid, in fact, could be just covered with dust and rocks that it's accumulated over 4 billion years of circling the sun. Whereas the interior might be mostly ice. Well, you would know that if the density turns out to be quite a bit lower than what you think the surface looks like. So here's the equipment that you need to do this. It's fairly simple. There's a big black box there. I call that my Oc box, occultation box, and I've now put together four of these. And battery and a video time inserter from IOTA, and a bunch of wiring, and then a Wattek 910HX very low light level video camera, which you can see hooked up to the telescope right back here. And with just, fairly simple equipment, you can record it. In this case, I was recording onto an old mini DV camcorder. And then it's software that does the magic to actually determine the timings of the disappearance and reappearance. So, in fact, classic example of where you could actually be doing very, very important work. This is an occultation of a very bright star by the dead comet or asteroid, or the transition object called Phaeton, which is the parent object for the strongest meteor shower of the year, the Geminids. And of course, we go through the Geminid meteor swarm, and therefore we go pretty darn close to Phaeton. And it is believed sometime in the next 2 million years, Phaeton will collide with the Earth. And its orbit needs constant monitoring because it's continually shedding stones and rocks and outgassing a little teeny bit. And those are all non-gravitational forces that then and they're a bit random, and so they require you to keep on top of this thing. Um, so we didn't really have a good idea where it was when this occultation was realized it was going to happen. And so we got 60 people, 60 observers with their telescopes to occupy every one of these little orange lines, all densely spaced, only a tenth of a kilometer apart. And we figured, though, the JPL orbit was probably the best, and that's in the middle here. And I've got a pretty good record of getting a success on these, and so they put me right in the middle. And lo and behold, I got lucky. And that's exactly where it was. And there's where Kirk Bender and I set up in the Carrizo Plain National Monument. And look at that. A very brief 1/4 of a second occultation when this very bright star, easily visible in binoculars, went bloop down to zero, and a quarter second later it came back. And there's the occultation with a comparison star and with, um, actually, I don't think I plotted the blank sky on this. And when we took the other observers and combined their data, we got this very nice ellipsoid shape for the, and of course, very precise position for Phaeton. And that allowed us then to now make future predictions for occultations much more accurately. And so we don't have to waste a huge number of observers who are probably going to see misses, including my friend Kirk Bender, who is right here, and he got a miss. So that was a great trip. And get you out under the night sky too. Very beautiful. So our occultation data and radar measurements from a close passage that it did earlier to the Earth. And that allowed us to get a pretty decent model. And it is now target for the Japanese Space Agency. They're going to send their Destiny Plus mission out to this object. And if they're going to do it accurately, they better know exactly where it is. And then I told you there was this nice occultation of a star, pretty dim star, really, Pluto, by Pluto. This is back in 2019, later in the same year as this last event. And now, what do all these lines mean? Well, every telescope here is occupied by an observer who is going to try to get the data. And that includes us right here in near Monterey Bay. And this is on Fremont Peak Observatory. The blue line is the predicted northern limit where Pluto would just be grazing that star. The red line is the one standard deviation limit within which we thought Pluto would occult that star. And I just want to point out that even after the New Horizons mission, which was at Pluto in 2015, here just 4 years later, we still did not know exactly where the limit to that occultation would be. So getting more occultations is always going to help in getting more data. Down at the bottom here, you can see all the different observers that got on the path to try and get this. Now, the really cool thing about this occultation wasn't only just getting a very good position for Pluto. Oh, well, there's our team. Uh, yeah, 15th magnitude, very, very faint. And there's a 30-inch telescope. When I'm talking to the kids, I don't like to tell them the mirror diameter because if I say a 30-inch telescope, they think, but my toys are bigger than that. What are you talking? That's not a big telescope. No, that's the diameter of the mirror. The telescope itself is way bigger. Anyway, I don't have to go into that, but I'll just say the big telescope, the big reflector, like I did right here. So there's me with my gear set up, and we're looking through the eyepiece right there. Nicely, Pluto is going through the summer Milky Way the last few years, and it's kind of getting towards the end of that period now, moving into Capricorn. But still, the star density is high enough that occultations, occultations by Pluto are going to get pretty sparse for another 100 years. So we better get them while we can. There's our reconstruction of the shape and position of Pluto. But that wasn't the best part of this mission. Best part was getting the atmosphere. So Pluto's atmosphere is incredibly thin, only 13 millionths of the Earth's atmosphere. And yet, the refraction, the differential refraction that light undergoes going through that very, very thin atmosphere is enough to easily see during an occultation. So there it is. And you can see that there's a flat part in the middle when it was totally behind Pluto and the atmosphere. But there's clearly these wings that are telling us actually the differential density of the atmosphere. So while there is noise in here, if you combine this with other data carefully, you'll find that the spikes I pointed out there are actually due to differential refraction and bending and focusing and defocusing of the starlight, and tells us a lot about the atmosphere of Pluto as it slowly refreezes onto the surface of Pluto as it's now getting farther from the sun. And then I got a little bit here on binary asteroids. So are binary asteroids are really cool because now we can find the masses. And this is just a nice visual of mm, Kirk and I tried to get this one, and we went through the pillars of Hercules, as the occultation people like to call it. We didn't get either one. We were we were in between. We were one of the lines that went in between. Oh well. But I have discovered, I first thing was the confirmation of the first binary asteroid discovered through the occultation method, and that was in 2021. Peter Nosworthy and Dave Galt, who are both active occultation people also in Australia, watched as this asteroid disappeared not once but twice. And since they are separate observers and separately in Australia, that was not only discovery, frankly, but also confirmation. However, to have confirmation of the confirmation, sort of the god of occultation astronomy, David Dunham himself, who's now getting pretty old but still active, alerted us that there would be another occultation by this same asteroid going through central California. That was the good news. The bad news, it was on a Wednesday morning at 3 in the morning, and it was all the way, it required a 200-mile, actually, a more like 250-mile drive, and no sleep that night at all. So I hesitated a bit, but I knew my inner child would then chime in and say, "We're going to do this." And so that's what we did. And we went out and we got it. And we got not only the parent, but the newly discovered satellite, and we got them even better just by luck than did the original discovery. And this is now the only asteroid, binary asteroid, with a very firmly determined orbit. It's the most carefully determined orbit, not just with these two events, but we've gotten a couple of other occultations as well. Yeah, so remarkably, there was another occultation by the same asteroid just 3 weeks later, and that also went through California. Um, and that was in not such a great place, the Sacramento River Delta, very windy. We did have very high winds. I tried to block the wind with this table that I mounted on my roof with some tape and whatnot. Shortly after this photo was taken, right after the event, the table actually blew down and whacked into me and my telescope. Danger to life and limb. We did get the occultation. It was a bit noisy, but we did not see the moon. And we've now later determined that the reason we didn't see the moon is because the moon and the parent object were basically blended together. But I was curious, and so I went through the calculations and figured out, well, where could this satellite have gone? And I figured out if the center of that asteroid was anywhere within those hatched areas, then we would not have seen it. And that's apparently what happened. Now, 3 years later, there was yet another Arecibo occultation, very high value, and it was on a weekend, and it was way out in the desert where I love to go. And so I clamored and I got permission to get a van from Cabrillo, and Kirk Pender and I took off, and we ended up in Needles, California, on the Colorado River. And there's a predicted shadow path for the parent and its little moon. And we even got a couple of other occultations that were a few hours before and right on the drive to get there. So that was pretty cool. One of those was a success. I got one occultation. Kirk's was a miss. This one had a challenge too because there was huge wildfires in California, and that's the predicted smoke path. And you can see that the asteroid shadow path was right inside the smoke path. So we were wondering, are we going to be able to see this or not? I decided, well, the odds were best if we just kept driving, and we went all the way to the Colorado River. So that was a big long drive from Santa Cruz, 1,000 miles by the time we were done. And we did get out, and in fact, the smoke plume migrated in the good direction, and we didn't really have any problem with smoke. We got the occultation. Kirk and I both had a success. And we both, however, were successful in getting the moon. And nobody saw both the moon and the asteroid, but there were a few observers, and mainly me and Kirk, and then David Dunham also got the main asteroid. And then this was the final observation that allowed us, now with 3 years of data, to get a very firm asteroid orbit for these two guys. And then now this is a very important mission. Um, I know I'm getting late here, but we're still under an hour, so I think we're good. The DART mission. So we're trying to test our ability to deflect asteroids if we find that they're on a collision course with the Earth. And so NASA developed the DART mission, and DART has multiple meanings, of course, but I forget the acronym. If you don't cook up a good acronym for your mission, it probably won't get funded. But this one did get funded, and it was a small pair. We wanted a small pair because we wanted to be able, first of all, we're more likely to get hit by a small object and not a big one, just by the numbers out there. But also, we wanted to be able to see a visible deflection with something that wasn't going to require, a nuclear bomb. We didn't want to take a nuclear bomb out there. But Didymus and his little moon Dimorphos are a known binary asteroid, very rare uh, to have a binary asteroid, but this one was identified as the best target, and so we sent a targeted mission out there. And the main part of the mission had all the cameras, and then there was a little secondary that we bloop sent out there to bang into Dimorphos. And then we needed to find out, well, what happened? Yeah, we took some pictures, but that's not going to tell us the orbit of the moon. If you're going to get the orbit of the moon, then you're going to have to, I mean, the mission ended pretty quickly because we weren't really able to stay there long. But now we're very much interested in getting any occultations that might be predicted for Didymus and Dimorphos. And so a few years later, well, it was a few years, I think it was about a year later, we had this nice occultation, a decently bright star, 11th magnitude. I know if you're familiar with magnitude, that doesn't sound very bright, but for our equipment, it's actually bright enough to be able to get very high cadence data, 1/60th of a second, and get pretty good data. But the asteroid itself was only less than 1 kilometer across. So we had to get inside this narrow little path. And the center line for the path is this yellow line. My campsite is right here. I set Kirk on this site right here, the other green line to the left. And there was a couple of other observers who journeyed out to the desert to try and get this. And lo and behold, we had a success. So there it is. The main, now this is the main body, not the little moon, but we had Norm Carlson venture out and get on the very edge where we thought the moon might be. And that was a much trickier thing. And frankly, it was risky. I mean, the odds are he's probably going to get a miss. But if we could get an occultation by the moon, boom, we would have now good positions for both the parent and the moon. And that would allow us to get a good um, orbit for the moon and calculate how much energy got deposited into Dimorphos, how much got turned into just rearranging stuff, how much of the stuff from the moonlet actually left. So a lot of aspects that have to get calculated accurately if you're going to know really what the energy of that impact was going to do. Unfortunately, Kirk did not get data on this because a power failure. But we knew it. We got good data. So I'm right there, and then we got two other chords on the main object. And look at that, we got right across the moonlet. So this was the first post-impact data on the new orbit for this object. So it's very important. And there's our camp. So we go out in the middle of nowhere, literally nowhere. And the science payoff. So there's a paper written on the object that we got the first confirmed binary, Arecibo. And look at what this interesting result is. The primary has a density of 1.6 grams per cubic centimeter. So for reference, ice is 1 gram per cubic centimeter. But the secondary, the moon, is a very different composition. It's only 1.2. So that's got to put important constraints on the nature of how this binary came about. They're not just two pieces that are separated. They're not, they had different histories. So the mystery continues. Okay, and now this one's very short because I know we're running out of time, but this is another very high value mission. This was the Lucy mission is on its way right now to the asteroids that orbit with Jupiter, the Trojan asteroids. They orbit 60 degrees in front of and 60 degrees behind Jupiter. There's stable little gravitational wells out there where stuff can collect, and we've never gotten a close-up picture of a Trojan asteroid. We're going to get our first ones next year, but we know that we're on our way to the biggest one, which is Euripides, and we need to know exactly where it is. And even more important, we need to know if there's any moons that might be around it, not only for, well, not only for trying to help us understand before it gets there what this object is, but also to keep our eyes peeled because we don't want to run into the moon and get caught, hitting upside of the head while we're photographing our cameras on the main object, and you can understand the problem. So turns out there was an occultation by Euripides in October of 2021, almost exactly 4 years ago now. A faint star, not very bright, 13.5 magnitude. Tough conditions. But look at the importance of this. We put out a lot of observers. NASA really wanted to get this event. So there was a ton of tracks that were set up. But look at the predictions from the weather. Not good. Should I commandeer my Astro 8A class, which was the night before? And well, there's no way that I could do both my normal class and still have time to drive from Santa Cruz all the way over the Sierras to Mono Lake and try and get this occultation. So I had to make a decision, and I'm going back and forth. No, it looks too cloudy. The odds are too low. We won't make it. Oh, maybe it will. Maybe it won't. Let's see if they've got an updated weather prediction. Oh my God, they've got an updated weather prediction. It doesn't look impossible. And the inner child says, you should go for it. So I called up Kirk and I said, Kirk, be at my place in 15 minutes. We're going for it. And off we went. And I should say, so that, talking to young kids in this way, they really get into the adventure of it. It's not just a bunch of lab coat people with their pocket protectors doing math. This is like, no, we're gonna get on our horses and we're gonna get out there and we're gonna get data. So there's all the tracks that were laid out. Most of them had cloud outs. However, I barely got a successful occultation. Kirk, I set up right on Mono Lake here on this track. Kirk had a cloud out, unfortunately. I was the next track up, this one here. It went right across a cemetery, an old, back in the cowboy days cemetery, which I hoped was not a sign of things to come. But here I am setting Kirk out at the Mono Lake Museum site at the parking lot. And there's me at the cemetery, and there's the Big Dipper in the background. And you can see clouds are coming, and those clouds are moving very fast. This is a storm front that's coming through, and most of the rain is happening on the near side, the coastal side of the Sierras. On this side, there's no rain, but there is still clouds and clear and clouds. Okay, the big moment came, and I could tell as the moment was coming that there was this cloud that was racing to run into the star. And of course, I knew roughly when the occultation was going to happen. And I said, you know what? This is going to be a dead heat. Somebody's going to win by a nose. Who is it? Am I going to get the asteroid covering the star first? Or is the cloud going to run it? Well, I lucked out by about 1/2 of 1 second. So there is the occultation by the asteroid. Boom, down to 0. And then after this, the cloud ruined all the rest of the data, including the reappearance. But that one piece was enough Because look, I was the only one to get data on the other half of the asteroid. That allowed us to determine the diameter. So now we know an accurate diameter for Euripides. And we know even better, we know now the centroid. So we know the position of it very accurately. So this is a big help to NASA so they can now do little mid-course corrections and make sure and plan out the mission accurately. This is the largest of the Trojan asteroids. So Kirk was clouded out, but we celebrated the team's success because I got a successful D by doing some aspen photography. Late October is perfect for that. And then we went to June Lake, had a beer, and got on our phones and communicated with the other team members. Getting home was dicey, but clearly we succeeded. Here I am. And oh, okay. Well, we still got a little bit of time if I can. Actually, you know what though? I should halt it here. This last one is in a sense the most important because now we've discovered a new moon around Quaoar. Let me just say very briefly, Quaoar is the first Kuiper belt object discovered after Pluto. And it has two rings, both of which are beyond the Roche limit, and they shouldn't be there. There should not be any rings outside of the Roche limit. Saturn's rings and Uranus and Neptune and Jupiter, they're all inside the Roche limit. Not these. Why? We don't know. But now we've got a new hint to add to it, and that is just 3 months ago, I discovered a new moon around Quaoar. So there's now two moons known around Quaoar. And we've got a new paper just accepted for publication in the Astrophysical Journal Letters that's going to be coming out. The initial paper is now already a couple of months old. And so we're going to try to figure out if there's some way that we can get an orbit for this. Actually, it looks very tough. This moon is so small, it's invisible for even the largest telescope in existence anywhere. I mean, not just on Earth. The James Webb Telescope isn't even big enough to photograph this asteroid, this new moon. So it'll be tough, but I'm working on it. Okay. So remember, like Indiana Jones, I'm working on it. I don't know whether we'll succeed or not, but occultations are going to have to be the way. Okay, anyway, there's some quick slides. But I should ask, is there any questions at this point? And I know this is really two put into one, but yeah, Jeff,
Yeah, hi. Thanks for the talk. Amazing work, by the way. And have you ever tried exoplanet transits?
exoplanet transits. Yeah, we did try one. We actually had a UCSC professor come out to Cabrillo because we had the right gear for it, but we got clouded out.
Oh, okay. Because
This was
have you heard of Exoplanet Watch? It's relatively new.
exoplanet watch. No.
No, yeah, it's relatively new. Only started like a few years ago. It's run out of Goddard now. But yeah, they're a group of exoplanet transit watchers. So
Are they looking for transits around known, well, let's say we already have maybe data from Kepler showing that yeah, there's planets here. Of course, I guess we know almost all stars have planets, so but you know, the alignment's right. And so now we're just trying to catch another one that might be within amateur reach.
yeah, and it's just like you said, defining those orbits is
Yeah,
really helpful for missions as well to save time, save money, all of that stuff. So
right.
if you haven't looked into it, it's called
Yeah, I'll look
Exoplanet
into
Watch.
it.
Yeah. Mhm.
I'll look into it. Thank you.
And just out of curiosity, how much did your rig cost? I'm assuming you kind of it looks like you kind of made a lot of it yourself, or
You mean
made a lot of
before
improvements at
Trump?
least. Yeah.
Uh, yeah, well, it was altogether about $2,500, but I'll bet it's more than that now. I think just the telescope has gone up by about 50%. It's about 2000 now just for an Celestron 8 SE telescope. Yeah, assembling the rest of the stuff was it wasn't homemade, but I did make the box. I did soldering and all that kind of stuff. There is actually, yeah, I should back up a little. There is a package made by an enterprising person in the IOTA mission. His name is Mark, and he's got the Astrid system, and that looks to be the most efficient way now. It's not quite as sensitive as the Wattec camera that I've got, but it's pretty good, and it's just much easier to set up. And all you need is a telescope after that. You don't need to have a camcorder. You don't need a computer. If you want to reduce the data yourself, then yeah, you'll need a computer. But probably everybody has a computer. The software itself is free, by the way. And the Astrid system is not that expensive. It's about $800. That's the camera and the recording gear and the GPS to get the time signals all in a very compact little outfit.
Thanks, and I don't want to hog it. If anybody else has questions, they should interrupt. But when you're doing this with students, or when you're sharing this data with students, if you had to guess, like, what percentage of them are like super super into it, and which ones are like, how many do you have to like drag by their fingernails, kind of thing,
Well,
just in your
actually,
experience?
Well, I
the
would never
question I
drag
asked in the
anybody.
chat goes off of that, Jeff, too. Rick, I was curious if you said this at the beginning, sorry if I missed it, but how much of this presentation was do in planetarium shows, and how much was just for this presentation, or is this all stuff that you would do in a planetarium show?
Well, I debated whether I should actually just show you my planetarium show, and I decided I wouldn't since it's your different audience, probably had different interests. But I showed you some slides that I do in the planetarium show. Um, but mostly I just go through all the planets and I go through the coolest photos that I can find for all the planets. But I thought, well, if I have like a high school group, okay, then they might really be interested in doing the science part. And I do have some dual enrollment high school and Cabrillo College students. One of them, um, uh, Jordan, is she's really interested in doing asteroid events. And I've got three other students who are very active in trying to do asteroid astronomy and are having some success. But they're Cabrillo students. Yeah. So yeah,
So,
mostly for the planetarium shows, I get elementary school kids, but sometimes I'll get older groups.
so I have a few questions maybe about the school group part, but
Sure.
before we start, since it's on the hour, I just want to make sure that if anybody needs to leave and wants to say goodbye, feel free to do so before we start back up with some more questions.
Sure.
And um, so a few questions about the planetarium part, because I was really impressed by the choice of your slides and the type of material you chose. So a couple of questions. One is, I wonder how much iteration you've done over the years to kind of refine it, and how do you make variations on that for different age groups? Is it mainly just like the younger elementary, or do you get like 5 and 6 grades as well?
I do get very occasionally, I'll get a junior high or high school group. Mostly it's elementary. As for changes, if there's a new mission with some really cool photos, then I can go in and swap out photos now really, really easily. Um, but yeah, mostly I'm looking for kind of, fun photos so that I can walk around the classroom and not the classroom, walk around the planetarium. We do have a very dedicated planetarium with circular seating and so forth.
Yeah.
Uh, we don't have to try and do this in a makeshift setup. But yeah, it's mostly elementary school groups. I can tune it if I really need to. I will always ask them, is there something in particular that you'd really like to see? because my standard show that I've worked up is, is the solar system, because that's what people can relate to. And it's groups that are not astronomy specialists, and therefore they're quite happy to just see really cool photos of the planets.
So the pictures were very colorful. Do you do any photo editing to bring out colors more than just what's straight off
Sometimes,
the
yeah.
image?
Yeah, so I have Photoshop, and you know, pumping the colors is something that every Photoshop person usually does just because. But I try not to go overboard because sometimes you can be criticized for that. Usually they're pretty processed before they ever leave, JPL. And so I may only need to size them and maybe crop them a little bit.
Okay. I know I'm guilty sometimes because it takes time to find really good photos of just using the planetarium equipment, like for the volcano on Mars, whereas having a photo up there as well really can make it much more effective for the audience, I think. So I think
Yeah,
even though you
exactly.
only have, I say only, but even though you use an A3P, I think a lot of the types of slides that you used are really good for other planetariums as well.
Yeah, I should say too, and I don't think I put it into the show, but I usually start out for the first 5 minutes and we just have the music and the stars so that their eyes can get dark adapted and they can see the stars. And I put it on daily motion. And so they can watch the stars moving across the sky, and I can show them where the North Star is, and I can show them that the stars aren't all just rising in the east and setting in the west, but they have their own different motions depending on what celestial latitude they're at. And then I can also show the sun migrating slowly through the ecliptic and give them a feel for the seasons. And that kind of thing usually is more, that last little bit is usually more important for the older groups, the older students.
Okay, thank you. So anybody else have questions about any part of this talk?
Rick, just your question about the hand controller you asked me before the talk was I did a quick search. The listing in the States were at 144 US dollars for a new one. And there was secondhand ones on eBay as well. You can search.
144.
Yeah,
Well,
143.
that's still within my microscopic budget.
Yeah.
So, um, however, this one student, I'm thinking, he's now developing a record of not being very good around equipment. I also gave him an Ock box and a telescope, and so he hasn't been able to get a successful occultation yet. And that part is, part of the learning curve, I guess. I've written it off to that, but when equipment gets wrecked, it's like, uh-oh, wait a minute, maybe I should rethink this.
Yes, I had that talking to one of the professors at the University of Auckland here, and his frustration with undergrads was he spent half the semester teaching them how to use the telescope before they actually did any real productive research work. And it was using
Yeah.
it was like a C8 or C9 or that, yeah.
Well, this person's pretty smart. He's an excellent programmer. He's actually now an intern at the Monterey Institute for Research in Astronomy. But he's also like a bodybuilder, and I'm just wondering whether the I don't know, that just the fines. Sometimes people are born engineers and sometimes they're born theorists. And in astronomy, I know both, and they know, and so they go to the right place, and they're good. But sometimes trying to do both is a expensive learning experience. Yeah. So yeah, this last slide, I thought tried to at least show you some cool slides at the end here, but Yeah, that's Kirk Bender at the big 36-inch telescope at the Monterey Institute for Research in Astronomy. They've got a really nice observatory at 1 mile elevation in the Big Sur Mountains. And we've now gone there 4 or 5 times for special events. And they make the most out of it. I can't believe how many power and data cables are coming out of the back side of that. It all goes into another room where they can monitor it. But when Kirk and I are using it, then we're right there at the meat end of the telescope.
Okay, so did you have more slides, or do people have any more
Well,
questions?
I can wait for questions and make sure we see all of them. I kind of wanted to show this one because look, there's the great comet of 2024, Comet Tushinen Atlas. And that's me, and that's the Monterey Institute for Research in Astronomy 36-inch telescope. And so Kurt Bender framed this one for me and got a pretty good shot. Um, yeah, so I did discover another moon entirely on my own by the asteroid Mart Schmidt, named after Martin Schmidt, who first understood quasars. And on hearing of my discovery, another astronomer, Jean-Francois Gaut, and also an astronomer in France, who had the right equipment to do photometry on the asteroid itself, started monitoring the asteroid. And lo and behold, the asteroid is actually undergoing mutual eclipses. So that was confirmation of the discovery and also is now allowed a very good orbit to be done because we were able to get the period without having to wait for another occultation. There was another occultation though, a few months later, and I thought I was even going to be able to get it. Appreciate how narrow these paths are. They're just a few kilometers wide. But there was another asteroid occultation by Mart Schmidt, and it too went right over Cabrillo College Observatory. I mean, the odds against that are like 1 in a million. And so I thought, wow, this will make a great second, write-up. However, we had to chase the clouds and try and get above the clouds, which we barely did. We barely got in front of the clouds. I mean, by like at 1 degree away, we got the occultation before the advancing cold front clouds got to it. And then this is taken a little bit afterwards. But we had to go all the way out to the middle of the Central Valley, another long, long drive. And I thought I wouldn't have to drive at all. But we got it, so there we are. There's our rock album cover photo.
So I have one more question, perhaps.
Okay, go ahead.
Of the people who work on occultations like you do, are many of them associated with small universities that have some observational astronomy aspect but don't have a large budget?
Well, I would say most do not have access that way, but a few do. If the star is brighter than 14th magnitude and the occultation is otherwise, relatively favorable, it's not right next to a full moon or, something bad. Um, Small telescopes, affordable telescopes, and the gear that I described can do it. And that's really the way most operate. The real problem with trying to do asteroid occultations isn't so much that you're not associated with an observatory, it's the fact that you're going to have to travel even if you are. Um, I've gotten what, maybe 3 or 4 occultations from Cabrillo Observatory, but I'm going to have probably a total of uh, probably 60 or 70 successful occultations this year, similar to what I had last year. And all of those are requiring me to get in the car and drive somewhere to get into the shadow. These shadow paths are very narrow if it's an asteroid of high value and importance. Once in a while, you'll have one of the big asteroids go in front of a star, and then you might luck out and you not have to travel. But also, those usually have pretty good, well-determined orbits, and so the scientific value is lower. Then, in those cases, you're typically just hoping to maybe discover a moon. So, unless you have a moon, you're not really going to have a clear idea of what this thing is made of, the bulk density. You need size and you need mass, and you're not going to get a good mass without a moon.
Thank you.
Yeah, so if there's no more questions, I do have just like 3 or 4 more slides if you're not bored yet. There was an occultation on June 25th by Quawar, and my plan was, oh, you know what? From Mira, it looks like the second and denser of the 2 rings of Quawar are gonna just graze this ring. These are 2 known rings that were already discovered by the big telescopes in Mauna Kea and elsewhere, and also by the James Webb Telescope. And from our knowledge of those rings, we could trace out at least a decently approximate path or where that would be. I really wanted to go to Lick Observatory. I tried hard to get on a Lick telescope, but they said no. We send out the time allocation committee. People make their decisions a year in advance. So no, we don't have the right equipment mounted on these scopes, and no go. And all right, well, this star is pretty dim. This star is 14.9 magnitude. We're not going to be able to get good data on this ring with our little 8-inch telescopes. But Mira's 36-inch could get good data, we hope. So I called up my contacts there and they said, yeah, come on up. But you could see Mira looked like it was going to get a miss. And indeed, we did get a miss. But more important, we got a complete occultation 2.5 minutes early that was not predicted at all. And so that was the big discovery, was here's something that we didn't know we were going to see. And it turns out that all the data shows it's not a ring, it's a moon. It's not a third ring. There are 2 known rings still, but now it looks like we also have 2 moons. Wewa, which we discovered many years ago, and then now this new moon, which I'll get to name at some point, but first of all, we have to recover it. Yeah, so they're fun. Occultations are a lot of fun.
Okay,
And
thank
that's
you. Thank you very much. I admit I didn't know much about occultations before this, so that was interesting.
good.
So we'll wrap it up. If anybody has any questions, now is the time to speak up. Okay, let's
Thanks again. Great talk. Yeah.
Go ahead.
Okay, thank you. I had fun.
Yes, so let's thank Rick for his time and his talk today. And we hope to see all of you again in a few weeks for Alan Gould's
Okay.
talk.
Very good. Thanks again.
Okay. Thank you, everybody.